many gauche interactions were present in conformer B? Gauche interactions, that means it must have been staggered. Okay, conformer B is over here. Let's label them. Gauche is defined by anything that is not next to an H. H's are the smallest things that they could be next to, so that's where they'd be most happy. So there's not, by definition, that's a zero sort of worth zero energy. It doesn't significantly contribute to the energy, in other words. So methyl ethyl, those are two non-H's together. So that's gauche. Methylfluorine, yep, that's gauche. Fluorine propyl is gauche. So this is not gauche, that's not gauche, that's not gauche. Okay, because that's the best it could be. All right, so we're going to say 0. Wait a minute, I didn't count them. What are we going to really say? 1, 1, 2, 3. So we're not going to say 0, we're going to say 3. Okay, so I urge you to kind of try this again without me, maybe cover the answers, and that way you can always come back and check. This warm-up, that problem was to help us get ready to put it all together to look at all the conformational isomers possible. So remember I talked about how we're going to have the 6 and really a 7th that's a duplicate that we plot. But we need some energy values to do this. So we're going to do this with ethane, then we'll take it up a notch by doing it with butane. Good practice would be doing hexane or pentane, even something else, okay? So some values we need before we make plots. We need numbers. So here's some numbers we'll use. Notice that the HH counts as 0. That is the smallest we could possibly get in terms of gauche interactions. It's going to count as, it's not a real true value, it's relative. So we start at 0. So for two H's to be next to each other, that's worth nothing. But if we have two methyls next to each other, that costs 0.9, and the units I'm using are kilocalories per mole. You might see something else like kilojoules or calories or something. So the numbers might be different, but relatively they'd be the same, right? So different books use different values, different units sometimes, but this is pretty common, kilocalories per mole for energy. All right, so HH, for them to be eclipsed, that's not, so HH is staggered. HH eclipse is worth, like I said, eclipse is a little worse than gauche, even big gauche. So that's, but look at this, a small difference, 1.0 kilocalorie per mole, but it jumps up to 1.5 when you have a methyl eclipse with an H instead of an H and H. So as the groups get bigger, the energy value gets bigger. And then we have methyl eclipse that costs the most out of everything possible in ethane. So that's the worst, right? All right, so we're going to actually calculate the total energy of each conformational isomer and plot them on an axis. So we are going to plot on the x-axis the dihedral angle. It's often theta. And on the y-axis, it's going to be energy. Total energy, though. So let's do a little tally before we need to have our total energy, because we might have more than one gauche interaction, right, or more than one eclipsing interaction. Before we can do that, we need to know how to draw all the conformational isomers of ethane. All right, so let's do that first. I'm just redrawing the Newman right now from the previous page. So we either have eclipsed, so ethane, remember, only is a CH3 and a CH3. So you either have eclipsed, okay, or staggered. You rotate all you want, they're going to match one of these. Okay, so let's calculate the total energy for eclipsed. These are the things we're looking at, eclipsed H's. Find that on the chart. eclipsing H's are worth 1.0 kilocalories each. 1.0 kcals per mole. 1.0 kcals per mole. 1.0 kcals per mole. Staggered. HH adjacent doesn't count as a true Gaussian interaction because it's worth 0. And that's all we have around the entire molecule. So the total energy is 1.0 plus 1.0 plus 1.0. We tally them all up, and I'll put my units on the outside of the parentheses so I don't have to do a lot of writing at a time. So this equals 3 kilocalories per mole. And the total E here is very easy. 0 plus 0 plus 0 plus 0 plus 0. So now we're going to plot it. And at this point, this is our first graph we're drawing. It's always kind of a surprise because you might have felt like this class was a little less mathy. We actually heavily rely on the consequence of math to make some predictions. So math is an essential interwoven sort of concept. So we're thinking about math conceptually, and actually organic chemists love graphs. So get comfortable with graphs because they visualize the trend for you. A lot, like a picture is worth 1,000 words, so is a graph. So students are sometimes surprised when I even get questions like, are we really going to actually do this again? And yes, that we will do it again and again and again and again and again. So let's get ready to jump in with that in mind. All right, the instructions said we are going to plot, and this is the way it will be for your plots and energy plots for dihedral angle. Energy on the y-axis in kcals per mole in this case. Dihedral angle on the x-axis, and that's also theta. Okay, I like to actually start at 0 degrees. That makes sense to me. Some start at 180. So when you look at a book, look at the x-axis and see where it's starting. But as long as you come full circle, you'll get the full picture. So 0 degrees here. And remember, we did those 60-degree increments. So 0 degrees is the two H's eclipsed, then they're staggered, then they're eclipsed, then they're staggered as we move around. So 0, 60, 120, 180, 240. And I'm not getting rulers out and making these perfectly spaced, but I'm trying to visually make them somewhat evenly spaced. Now we get to add the dots for the values. We only have two values. It's either 3 kilocalories per mole or 0 kilocalories per mole. And so think about ethane. You can even grab your model back out, or maybe I'll use the huge one. As we go around, 0, 60, 120, 180, right? But we've worked out that staggered for ethane is always worth 0. Eclipsed is always worth 3. So when they're 0 degrees, they're eclipsed. Like so, right? Let's say we're even tracking this particular one. This one versus this one. So those are 0 degrees. And then if we rotated by 60, if those are our reference H's, then we'd have 60 degrees dihedral angle, 0 energy value. So at 0 degrees, we have 3 kilocalories per mole. 0 degrees. Oh, let's add our energy values here. 1, 2, 3. So at 0 degrees, we're at 3 kilocalories per mole. Then we're at 0. When we rotate again to 120, we're eclipsed again. So we're high energy. 3 kilocalories. 180, staggered. 0. Eclipsed, staggered, eclipsed. Only two energy values possible, 0 or eclipse, because 0 or 3, because of the fact that we have so few distinctions on ethane. So many of the same groups. And we connect the dots and we have our energy profile. By looking at that graph, I can tell a lot. What if I didn't know that was ethane? I could tell a lot about it. I could say, look, I only have two values. The minimum is always 0. The maximum is always 3. There's no global minimum different from a local minimum, right? We have the same minimum and maximum no matter how I rotate those bonds with respect to each other. But that's not going to be the case anymore. We are not going to have a plot that looks like this again. We should expect local minima, local maxima, global minima, right, versus the global maxima, because not all values are the same when we have staggered anticoplanar versus staggered, eclipsed coplanar versus staggered anti, right? They're not going to be the same as the staggered gauche. So when two of the H's on here, those green and blue, if we switch those out for two different groups, or even two of the same groups that are not H, then we have a different looking profile. So it's natural to just kind of go up to butane. So go ahead and build butane. Take a minute to do that right now. Build butane. Take your ethane. Save those methyls. Don't start from scratch. Get 2 carbons to make a CH2. And just take out a bond and add a methyl on the other end. And there, now we have a butane. I want you to follow along. You need to do these rotations. We are going to draw all of the possible conformations of butane down the C2-C3 bond. So in other words, butane one, 2, 3, 4. Your eye is looking between carbon 2 and 3. Let's bring this down a little. Okay, so that means we're going to pay attention to the dashes and wedges with the H's. Fill those in. And notice these are methyls. I'm going to say Me to emphasize. Those are not just little lines. Those are big groups, big bulky groups. Now, we like this zigzag notation as our default for drawing an organic molecule for a reason. Notice that these methyls are anti to each other. They are staggered anticoplanar, and they are the biggest groups. This is why we draw the zigzag as our planar component. But anti is not the only way it exists in solution. There's actually free rotation, and but listen to that noise. You hear that? Do that with your own model. If you don't hear it, move your methyl, because these also rotate around the methyls and rotate around the C2-C3 bond. Those methyls are literally bumping into each other. The sound of that means it does not spend a lot of the time in the conformation shaped like the U, where my methyls are here. It spends most of its time anti. But it still can rotate. When it's warmed up in solution, they're all going to rotate, right? So all these bonds are rotating. They're even stretching, bending, doing other things, but that's part of their, they don't sit static in the solution. They rotate. So we need to understand, we can make predictions. Where does it spend most of its time? But does it ever rotate that way? Yes. And what can we do to take advantage of that? So let's analyze its rotational patterns. Let's start at 0 degrees again. What does that mean? That means the methyl won't look like this. We won't have the zigzag, we'll have the U shape. In other words, the methyls will be eclipsed. So in order for them to be 0 degrees, so let's go ahead and do the Mercedes-Benz sign this way, and then have them lined up. In order for them to be 0 degrees, that means the methyl is next to the methyl. And then everything else is H's, so this is actually fairly simple to start. Okay, so this is 0 degrees. Then take your model and do this with me. So we have the methyls together, 0 degrees. Now we're going to rotate I'm going to rotate, you know what, just for fun, I'm going to rotate the front this time, because you can do that too. Okay, you can also rotate this way. It doesn't matter. So just to follow along with me, I'm going to rotate the front clockwise. So let's do a rotation by 60 degrees. That means keep the back the same in this case. And now we're, instead of being eclipsed, we will be staggered. All right, so I have staggered, I have eclipsed. You should always alternate if you've done one 60-degree rotation. And now we're at 60 degrees from each other, right? And that's a gauche interaction right there. We started off at eclipsed. Now we're at staggered. And there's a gauche interaction right there. Okay. Rotate again. Now you can rotate the front or the back, but you're going to get confused if you rotate the back now, because I made a decision when I started to keep the back the same. And it's always advisable to stick to that. Otherwise, it's really confusing if you start rotating both. So keep the back the same. Because I have already moved the front, the back will stay the same the entire time. In fact, maybe even just to stop us from accidentally doing it, let's draw a bunch of these. We're going to draw 7 total. And so go fill out your 7. One, two, three, four, 5. All right, and then why don't we fill out what we know about the pattern? I like to do the brainless stuff first so that I don't make a brainless mistake later. So we know that we're going to go staggered, eclipsed. With every motion, it alternates staggered, eclipsed, staggered, eclipsed. Okay, so why don't we fill that framework in? Then we'll fill in the missing groups on the bonds. So I will have eclipse now. So the front one will be eclipsed. Then I will be staggered again. Then I will be eclipsed again. Then I will be staggered again. Then I will be eclipsed again. Was I doing that before? Here, right here in the front. There we go. Now let's fill in all the things that matter. Now you stop and your brain has to work. Say, okay, I kept the back fixed. My methyl used to be here. I'm going clockwise. Now it's going to be eclipsed with that H. So I go down another 60 degrees. Okay, so now my methyl's here. I'm going to go 60 degrees again. It's going to be right here. Opposite, it's going to be staggered. And so now there's my methyl. So the rest are H's. Then continue around, you know, it's kind of like the clock face. Methyl is now eclipsed with another H. Methyl is now gauche to that methyl. And we end with the methyls eclipsed again. Let's label how much we rotate, what those methyls are related to each other. 60, 120. Then we went to 180. Plus 60 degrees is 240. Plus 60 degrees is 300. Plus 60 degrees is 360. This is everything possible. That's full circle. Some of these are the same. You might say, wait a minute, I know 0 and 360 are the same. And that's okay, they really are. We're just doing this for completeness for the sake of doing it on the plot. Time to tally up the values. So let's do an energy tally. Going back to those values that were in that chart here, okay, we're looking at eclipsing CH3s to start, because we started at 0 degrees. Eclipsed coplanar. So that was the highest energy value. This was worth whopping 4.0 kcals. Eclipsed H's are 1.0, 1.0 kcals, per mole. Sum that all up. 4 plus 1 plus 1 equals 6. Okay, next one. What value? So 0 degrees. 0 kcals per mole. 0, 0, 0. What's left? Only that gauche interaction. That's worth 0.9 for 2 methyls. By the way, you don't need to memorize these numbers. Tables are always given, but you do need to know how to calculate the total energy value, given different numbers even. Okay, now let's go back to eclipsed. However, this time we are not using that whopping 4.0 value because the methyls are no longer eclipsed. The methyls are eclipsed with H's. Okay, so we already remember, if you remember, this was 1.0, the H's and H's eclipsed, kcals per mole. What about H in methyl? Do you remember that number? No, we haven't used that yet. H in methyl is 1.5 kcals per mole. Okay, let's do that again because that's the same, 1.5 kcals per mole. Oh, total. So 1.5 plus 1.5 plus 1.0 kcals per mole for total, right? All right, now we're at 180, where the methyls are anti each other. And remember that being next to an H counts as nothing. So this is 0 again. Nice, right? That's clearly the winner. But it's nice to know where the others fall in place. Okay, so now we're back to eclipsed. But we're on the other side of the clock now. We've worked our way around half the clock. And if the molecule is symmetric, which this is, you start to see the same values pop up. But we're going to be thorough and look at that afterward. So methyl eclipsed with H, methyl eclipsed with H, H eclipsed with H. That sounds familiar. H eclipsed with H is worth 1.0 kcals per mole. Methyl eclipsed with H was 1.5. We just did this. 1.5 kcals per mole. 1.5 plus 1.5 plus 1.0 is 4. We see it just before. So in other words, the 120 degree dihedral angle is equivalent to the 240 dihedral angle in this case, because notice this is the same as this. It's just a mirror image right here, right? They're worth the same energetically. Methyl H eclipse, methyl H eclipse. Methyl H eclipse, methyl H eclipse. HH eclipse, HH eclipse. Can we save ourselves any work by finding any others that are the same? How about methyl, methyl, gauche with nothing else? Well, we've already looked up methyl, methyl, gauche, but we've done this before at the 60 degree. So the 60 degree has a methyl, methyl, gauche with no other values to contribute. The 60 degree dihedral angle is therefore equivalent energetically to the 300 degree dihedral angle. That makes perfect sense because 300 is 60 degrees away from 360. 360 is the same as 0. So therefore 300 is analogous to 60 in this case. Okay, so since we know 360 is the same as 0, everything eclipsed in the worst possible way ever is the highest energy value of 6. So we go use that again. Okay, that was the hard part. We're ready to plot and connect the dots. Let's go do it. I'm going to use these numbers. That's those dihedral angles are my x values. Those red numbers are my y values. Energy goes up. And we are reporting that with our units, kcals per mole, in parentheses, dihedral angle along the x-axis. Okay, now, I like to start at 0 once again, but it's not mandatory. 0, as long as you go the full circle. 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300 degrees, 360 degrees. In blue, I'm going to put our coordinates. At 0, oh, I didn't fill in my x-axis again. 1, 2, 3, 4, 5, 6. 0, we have our value of 6. I didn't go higher than 6 because that's the highest we had. At 60, we have a value of 0.9. I'm going to cheat and just put it close to 1 because we're really looking at overall trends, not pulling out the graph paper and using a ruler to line it up. We don't have another value that's 1 or close to 1, so we can get away with that. At 120, we're at 4 kcals per mole. At 180, we're at 0. Nice, again. Now 240, remember, matched 120, so we're back here. Remember that 300 matched 60, so we're there. Remember that 0 matched 360, so we're way up here again. So let's connect those dots here, up. Whoops, got a little wild there. Do it again. Way down there, back up. Interesting. Now that plot looks different. And it looks different than the one above it. In fact, I see that it's not the same maximum every time or same minimum. Let's label some features. There's our global minimum. Here is a local minimum. Our global max is at the 0. Here's a local max. And notice it repeats on the other side. So if we draw this dotted line here, we'd see we could fold it and get it to match. That means there's a plane of symmetry there. We could slice it in half and see that they're basically looking in the mirror. So you'll notice something else is if you take the 180 one and look at any two flanking it, these are mirror images. So these look like, hello, I'm looking in the mirror if I look at you, right? These are also mirror images, methyl, methyl, gauche, looking at methyl, methyl, gauche. So that's reflected in the plot as well. The shape of the plot has mirror symmetry here. Okay, so that plot tells me that those corresponding Newman projections are indeed symmetric. However, it also tells me this is not ethane. I could look at that and say that can't be ethane because the global minimum is not the same as the local minimum, right, over 300. I urge you to practice butane, or excuse me, step it up to hexane maybe. Give that a try and see what you come up with. Good luck.